we're going to cover 9.1 and 9.2, stratospheric ozone and ozone depletion. So by the end of this lesson, you should be able to explain the importance of stratospheric ozone to life on Earth and describe chemicals used to substitute for chlorofluorocarbons, or CFCs. To accomplish this goal, we will describe the function of stratospheric ozone, describe current solutions to stratospheric ozone depletion, describe the purpose of the Montreal Protocol, and identify the CFC replacements. So, the main character in our story today is ozone. So, you're going to want to make sure on the AP exam that you're always identifying the type of ozone you're talking about, because ozone in the stratosphere up high is good. Ozone nearby, in tropospheric ozone, is bad. So ozone is neither good nor bad. It depends upon where you're finding it. Kind of like a sunscreen. So in the stratosphere, ozone blocks a lot of UV light. So we've got UVC, UVB, and UVA. These are the ultraviolet lights coming from the sun. UVC is high energy. And then UVA is the low energy. You can see that the ozone layer is filtering out all of the UVC, most of UVB, and some of UVA, because we do need some UV light down here. So the ozone layer up high is good because it acts as a sunscreen. It's protecting the Earth from those damaging UVC rays. But we know that when it's in the troposphere, down here, that the ozone leads to tropospheric ozone and asthma and other health problems in people. So just like sunscreen on your skin is good. If you eat the sunscreen, very bad for you, so don't eat the sunscreen. That should be your big takeaway here. Don't eat the sunscreen. So why do we care about the stratosphere having an ozone layer? Because it filters out that UV light, and UV light can cause cataracts in the eye. So this is an example of a cataract, which greatly reduces your vision, kind of makes it pretty cloudy. And it also leads to more cancers as a result of the UV exposure, because the UV exposure damages our DNA, which leads to changes and cancers in both people and animals. This can happen. In this chart, we can see that this is the numbers of melanomas as a result of UV exposure above normal. And without the ozone, you can see that poor Australia has very high levels. So their levels are high anyway, but if we didn't have an ozone, they would have seriously high levels of UV exposure and, as a result, higher than normal levels of cancers. So ozone up high, good for us. However, enter the bad guy. That is our chlorofluorocarbons. So chlorofluorocarbons have two chlorines and two fluorine atoms. They're found in aerosols, or they used to be found in aerosols like hairsprays and refrigerants to keep your refrigerator cold. And what we discovered is that chlorofluorocarbons, when they get into the atmosphere, they last for a very long time. So they don't go away very quickly, and they cause depletion of the ozone layer. So we say that there's an ozone hole, but it's not exactly a hole. It's just a thinning of the ozone layer, which allows these harmful UV light rays to get through. So if we look a little bit closer here, we see that the chlorofluorocarbons, you can just use the abbreviation CFCs, but you should know what it stands for because the AP test may say it both ways. But when you're writing about this in an FRQ, you can just write CFCs. So the chlorofluorocarbons, when they interact with the sun's ultraviolet rays, are broken down into chlorine atoms. So we have our CFCs that go here. Ultraviolet rays break them into the chlorine atom, which when it interacts with the ozone, steals away an oxygen. So it steals away an oxygen, and now instead of having the O3, we've got just regular O2 gas. And our chlorine now has an oxygen attached to it, which then snatches up another oxygen, so then we get Cl2. And then that eventually breaks apart, the chlorine atom gets released, it goes back to the beginning, and we have a continual cycle. So it comes back to this point, the chlorine atom is free again, steals another oxygen, then takes another one, then it gets to become ClO2, then gets recycled back into this continual cycle. Again, if we go back here, we see that they lead to that depletion in the stratosphere and the ozone. So, how do we fix the problem with chlorofluorocarbons? Enter the Montreal Protocol of 1987. So the best solution was to ban CFCs. So what the Montreal Protocol did was call for a global reduction and eventual phase out of these chlorofluorocarbons. But as I mentioned, the CFCs stay in the atmosphere for a very long time. So we still have this ozone hole, and it will take until the mid about 2060 before we're going to see a close up of the hole in the ozone. So we need to talk about the replacements for chlorofluorocarbons, and we replace those with the hydrofluorocarbons. We can see in the graph here that the CFCs increased until right about here is 1987. We asked for that global decline and eventual phase out, and then our hydrofluorocarbons are showing an increase. And this is great because it worked. But the problem is HFCs are almost just as bad as CFCs, but instead of being a problem for the ozone, they're a strong greenhouse gas. So to summarize this, our goal was to explain the importance of stratospheric ozone to life on Earth and describe chemicals used to substitute for chlorofluorocarbons. What we discovered is that stratospheric ozone is a necessary sunscreen to prevent cataracts and high levels of skin cancers. We used to use a lot of CFCs, which stole the oxygen from O3 and deplete the stratospheric ozone layer. But things got better when we implemented the Montreal Protocol. However, now we use HFCs, which are also bad, but just in a different way.